All right, so we're working with Chapter 7, Sampling Distributions. Before we dive into 7.2, let's talk a little 7.1. This happened now before break, so I'm going to try to kind of help again, get it back together here. So here's what we talked about before break. See if this makes sense to you. Just kind of soak this in a little bit. Let's say that we had a population, and that population was Lake Ridge High School students, okay? And I want to go into Lake Ridge High School, and I want to take a sample, so I'm going to do little n, of size 30, all right? So I go to Lake Ridge High School. It's a big high school, right? We have about 1,200 students. I'm going to randomly take 30 of them. And maybe the question I really want to know right now is, do you drive yourself to school? Do you drive yourself to school? So I'm going to ask every single student, do you drive yourself to school? They're going to answer yes or no. And with that, we will get a proportion. So let's assume that I went in, I got my sample of size 30, and I got my sample proportion. Remember, we used a symbol for that in 7.1, and that's p hat. And let's say 40% of my sample said, yes, I drive myself to school. So that's kind of the first big thing. We took a sample, we found the proportion, we got it. So now I could, if I needed to, go to superintendent or school board and be like, hey, 40% of Lake Ridge drives themselves to school. And that would be kind of an accurate assessment, but it may not be truthful, right? Because that's just the sample of 30. And now what we're hoping is that sample of 30 is a good representation. But what we talked about is sometimes that may not be good. Even if I did a random sample and I got a proportion of 40% of the students driving themselves to school, doesn't necessarily mean that 40% of the population drives themselves to school. What it is, it's a good estimate of what could be happening. So we said in chapter 7.1, let's build a thing called a sampling distribution. So what I would do, I would create a dot plot. I'd find 0.40, and I would put a point right above it because that would represent this one sample here. And I might call that the first sample, because then technically what I would do is go back into this population of Lake Ridge High School students, take another sample of 30, get a new proportion, we'll call it proportion 2, and find out what the proportion is of that second sample. Let's say it's 0.75. So what I would do, I'd come over to my dot plot, and I would plot it, and that would be it. And then we would continue this over and 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 over again, and we just keep doing it. And what that's going to do to my dot plot is it's going to put a bunch of dots all over this dot plot, right? And then we're going to just keep this going, right? So then my dots start just kind of being all over this dot plot here. And they should start to stack up, though, at some point. And what should happen is that these dots really start to kind of point us towards the real value of the population because they start to really stack up tall over one single value here, right? And so the idea here is I take as many possible samples as I can and plot them over here. And what this thing then is called is a sampling distribution. That is my sampling distribution. It is all possible sample statistics plotted on the same plot or on the same graph, and it gives me a sample distribution, right? So that is what we talked about in 7.1. We also talked about, you know what? If this lines up correctly and it lines up perfectly over the true population parameter, we would call it unbiased, right? And remember, unbiased was when the average of all these samples equals the true population parameter. We call it unbiased. So there's a little bit of that is a super quick recap of what we did back in 7.1. But this idea of sampling distribution, this notation, the P with the hat above it means the sample proportion. If I gave you just the P without the hat, that means the population proportion, right? And so just identifying and distinguishing between those two, All right, so that was your 5-minute recap right there of the 7.1. So let's get into 7.2. So let me give you some things to think about real quickly, and then we'll do a problem together. All right, so 7.2 is called sampling distributions of sample proportions. So I'm just going to do it of the p hats here. Now, let me just kind of really boil this down. Here's what you need to know for 7.2 is we need to be able to create this sampling distribution. But if you recall, I would have to take like 1 million samples and plot them on the same graph in order to create sampling distribution. And that would be exhausting, because if I did that for every time I wanted to know something about a population, we would get exhausted with it. So what we want to do instead is say, what if we took 1 million samples and built this sampling distribution? We ask ourselves a question. What shape would the distribution be? What number would we center the distribution around? And what spread value would the distribution have? These are all theoretical in nature, but as long as certain things check out, we know that theoretically it's going to make sense. So here's one thing I might have you do is pull out your pink sheet, your notes, or sorry, your formulas, and let's take a look at the second page where it says sampling distributions. And matter of fact, we want parameters of sampling distributions, and we're talking about the p hats right now. So this is the part I want you to look at, because what we're going to steal from this is the formula for mean and the formula for standard deviation. And we're going to use that to help create our curve of sampling distributions. All right? So if you got your pink sheet, go ahead and grab it just so you can see it. You can mark on it. That way you can see what it is, because I'm never asking you to memorize these. I'm only asking you to know where they are in the formula sheet so that you can access them. Okay? So that is where we will start the sampling distributions of p hat. Okay, let's start first with number 1. What is the center of my sampling distribution of p hats? Well, by formula and by definition, we would say that if I averaged all those p hat values, it should equal the population parameter. That's exactly what the formula says on the formula sheet. But this is only true if the condition of random sample is checked. Okay? So here's actually what we're doing in 7.2. We are going to be able to use a certain formula if a condition is checked, because we are taking it from literally taking 1 million samples out of a population to theoretically what should happen if all things check out like they should. So what we will do, we'll check to see if there's a random sample. That makes my sampling unbiased. And then I know that I can center my curve around P. So that's going to be one thing. So, okay, now we know the mean. After you know the mean, what do you need to do? Well, you need to know the standard deviation. So the standard deviation of all the p hats is equal to the square root of p times 1 minus p over little n. And that's all underneath the square root. That is straight from the formula sheet again. That is where we will find our standard deviation. But this only occurs if the condition of independence is checked. Okay? So a standard deviation formula only works if everything is independent, if every probability calculation is independent, right? Otherwise, it breaks down. So we have to check for independence. Let me tell you a problem here. The problem is most of the time, the independence check is violated. Now, what do I mean by that? Think about a deck of cards. If I were drawing cards out of a deck of cards and I do not replace the card, then every time I pull another card, it is dependent on the card that I pulled first. So we would call those not independent if I'm pulling cards. If I'm pulling marbles out of a bag, but I do not put the marbles back into the bag, then those are dependent, right? Because I didn't put the marbles in the bag. So every time I reach in and grab another marble, the probability keeps changing. So this is a situation in which the condition of independence gets violated. It's the same way when you're dealing with people. Let's say I went to Lake Ridge High School and I took a sample of 30 people and I'm asking them, do you drive to school? Well, every time I talk to a person, I want to know, do they drive to school or not? And I don't want them to go back in the population because I don't want to select them again. So I actually literally keep them out of the population, which then violates independence. So if this is violated, it's going to actually be okay as long as you don't violate the independence too badly. So what we mean by that is we are going to violate independence, and we know that, but we have to have another rule. So statisticians kind of came up with, says, well, how big of a sample can you get and still have an accurate standard deviation? Or in essence, that standard deviation calculation that we just wrote down right there still will work for us. So it'll look kind of like this. If my population size, capital N, is always greater than or equal to 10 times my sample size, then we're okay. So this is also known, AKA, the 10% rule. As long as my sample does not exceed 10% of the population, this will work. So you want to write this down. This is the 10% rule. This is going to be important to us, that if we're violating independence, which is usual, then we just have to make sure that when we multiply our sample by 10, it still is underneath the entire population size. If that's the case, that calculation is going to work just fine. Okay? So again, check the condition, use the formula. Check the condition for mean, use the formula for mean. And then thirdly, we will just need to know, what shape is this graph going to be? Well, here's the deal. I believe this will be approximately normal. And this is going to be good if it's approximately normal because we know how to work with normal curves. So it'll be approximately normal if the condition of large samples is checked. So what do we mean by large samples, right? Okay, large samples, here's the check we need to do. Sample size times population proportion, make sure that's greater than or equal to 10. So this is another threshold value. And we also need to check that the sample size times 1 minus p is also greater than or equal to 10. Okay? So these are called large samples because we need to make sure that our sample size is large enough when compared to the proportion, and it maintains a threshold of at least 10, right? If these are true, then we know that we're going to be able to use the approximately normal curve to estimate or theoretically set up our distribution. So really, here it is. If I were to show you this is 7.2. It is how do I set up a curve, but also verifying that we are allowed to set up a curve, right? Think geometry when you did proofs, when you did if-then statements, where you had to say, if this is true, then I'm allowed to say this. So if the random sample is true, then I'm allowed to use this formula. If the 10% rule checks out, because we're probably going to violate independence anyway, then I'm allowed to use this formula. And if the large sample counts are checked, then I'm allowed to use the normal curve. And that's it. This is what 7.2 is. Once we get past that, it's no longer 7.2. It's really doing chapter 2 work. All right? So pull out your little half sheet of paper, and this is what it says on it, warm up 7.2. Let me walk through this with you just so you have a good example and then use it to run with, okay? So here we go. So with the following on this, they want us to do three things first. Find the shape, find the mean, find the standard deviation, and go ahead and check the conditions. So we'll do all of that. And then once we've done that, we're gonna set up the curve, draw the curve, shade the curve, do all the stuff that we normally do with a normal curve, okay? So here is the question. Suppose that a particular candidate for office is in fact favored by 48% of all registered voters. This, my friends, 48%, is a parameter. So we're gonna say the proportion of the population is 0.48. I always like to change percents to decimals. It's just gonna make life easier. Okay, so what else do we know, right? Is all registered voters in a sizable metropolitan district. So that's really the main piece right this minute. Let's continue on. A polling organization takes a SRS of 500 voters. So remember SRS, that stands for simple random sample of 500 voters. So they're telling me that N is equal to 500, okay? And we'll use the sample proportion to estimate the population parameter. Okay, so that's all we really need to know because those are the big things. Now, there is the question, what is the probability of the sample proportion will be greater than 0.5, causing the polling organization to incorrectly predict the results of an upcoming election? Well, I think what we need to do is not worry about the question yet. Let's worry about the setup. So let's look at number one. Number one, it says find the shape of the distribution. Well, let's do this. The shape is approximately normal. But let's just go ahead and give a little check to make sure that it is. So look at our notes. How do we check? We take N times P and make sure it's greater than or equal to 10. So is 48% of 500 greater than or equal to 10? Yeah, it is. I don't even need a calculator for that. I just know. And we also want to take 500 times 1 minus P. So I'm going to take 1 minus 0.48, that's 0.52. Make sure it's greater than or equal to 10. Is it greater than or equal to 10? Yeah. Again, don't need a calculator to help out. I think I got that one down. All right, there's number one. Number two, it says find the mean of the distribution. Well, we believe that the mean of the P hats will equal the P value of the population, which is 0.48. But we need to be sure we can check that, right? Check or verify that. Well, what do we need to check? We need a random sample. Hey, guess what? They said SRS, which we know stands for simple random sample. So yes, I'm gonna put a little check mark next to that. It checks out, therefore it's unbiased. Therefore we can use that formula. Okay, let's find the standard deviation of that. Standard deviation of the P hat is square root of 0.48 times 1 minus 0.48 divided by sample size, which is 500. Okay, I'm gonna now use a calculator real quickly to check this real quickly. All right, square root of 0.48 times 0.52 divided by 500, all underneath the square root, good, 0.0223. Okay, let me check to make sure that that is true. So the check, I'm gonna use the 10% rule because we are sampling people, therefore you are pulling them out of the population. So the check really has to be toned down to the 10% rule. Now, here's the deal. I do not know how many people they're talking about in the population, but what I have is some words, so I'm gonna use the words. All registered voters in the district. Now, it does say a sizable metropolitan district. So think like Portland area, think like Multnomah County or Clackamas County. Do we believe that there's greater than, I'm gonna take my sample and multiply it by 10, it's gonna be 5,000. Do we believe that there's more than 5,000 people in that sizable metropolitan district, I'm going to do this, but I'm also going to put the words safe to assume. Because we don't actually know for a fact, but I'm going to take some of my logical assumption making and assume that, yes, that can be done. So there it is. There's the first three. That is 7.2. We have claimed the shape, we know the center, and we know the spread. So now number 4, when it says draw the curve, shade the curve, find the z-score, answer the question, we can do all of that, right? So we know this thing is going to be approximately normal. We checked and verified that. We know that it's going to center right above 0.48. We checked and we verified that. And then we know how wide this thing is going to be because we have its standard deviation sitting up there. And I could label these out if I wanted to. I don't want to right now, okay? So we got all of that. So now let's get to the actual question. The actual question says, what is the probability that the sample proportion will be greater than 0.5? So let's find 0.5 on our curve, 0.5, and it said greater than. So we are shading this side over here. And we're just trying to find out what is the probability of what we just shaded, because that would answer the question, right? Now it also tells us to go ahead and do a z-score. Remember how to do a z-score for this. We're going to take z equals my value, 0.5, minus the mean, 0.48, divided by the standard deviation, which is 0.0223. And so I am going to get, if I do that in my calculator, 0.5 minus 0.48, and then divide that by 0.0223, I get 0.8968. So let's go ahead and round that to 0.90. So remember, a z-score tells you how far you are above or below the mean. So in this case, I'm not quite a full standard deviation above the mean, but I am 0.9 standard deviations above the mean. But let's finish off the problem. Now, so I could use that z-score and go look up from the pink sheet, or I'm going to go normal CDF in my calculator. I'm going to put 0.5. I'm going to put infinity as the upper bound. I'm going to put 0.48, and then I'm going to put 0.0223, right? That's my standard deviation. And it's going to give me a probability, or the area that I am shading. So let me enter all of that into my calculator real quickly. Okay, and I'm going to get 0.1849. So about 18.5% chance that I get a sample. Remember, because this curve represents, remember, a million different sample p-hats underneath here, right? We're just theoretically shaping it up for what it should be. So it's saying that there's about 18% or 18.5% of them lie in that region, or that is the probability that I grab a sample that'll give me a p-hat in that region. So there you go. That's what you're doing. So 7.2 is all about this setup and checking and verifying, and then it leads into chapter 2 work, which is solving normal curves, all right? So that's really where you can end it, and you can just start working at this point. If you want to, here is one more example. I will do this with you real quickly, or just do it, and then you can, if you want to do it, do it. If you don't, and you're like, hey, I got this, I'm ready to run, rock and roll and run with it, okay? So here we go, identify the mean of the sampling distribution. So I'm back up in this, right? Suppose 75% of young adult users watch online videos. A polling organization, a simple random sample of 1,000 young adult users, and calculates the proportion in the sample who watched the online video. So identify the mean. So I'm going to go back to the mean of all these proportions should equal the mean of the the proportion of the population. But let's just check real quick. We always need to check. There's those magic words, simple random sample, check. We're ready to move on. All right, calculate, interpret the standard deviation. So I'm going to take the square root of 0.75 times 0.25 over 1,000. Okay, now let me calculate that real quick. 0.75 times 0.25 divided by 1,000. And I get 0.0137. Okay, so I'm going to round it to 137. You could round it to something different. That'll just change a couple values at the end, but no big deal there. But we got to check, am I allowed to do that? Remember, the standard deviation needs independence. We are violating independence when we are sampling, so we need to check the 10% rule. So 10% rule, so I'm going to say this, I'm going to use words here, all adult internet users, right, that's who we're talking about, is greater than 10,000. Now here's the deal, because I'm taking 1,000 times 10. I don't know what we're talking about. Are we talking about the state of Oregon? Are we talking about the United States? Are we talking about the world? Who knows? So we're going to, again, put a little check mark here, and I'm going to write the words safe to assume, just to make sure that you know I'm assuming that there's more than 10,000 adult internet users out there, which seems pretty good thought there. Okay, let's do the next one. I believe that the shape should be approximately normal in shape, but we got to check. Check the large counts, or the large sample size. So here we go. We're going to take sample size 10,000 times the proportion of the population, make sure it's greater than or equal to 10, and we'll take 1,000 times 1 minus the proportion, make sure it's greater than or equal to 10. Guess what? Both those numbers are greater than or equal to 10. Therefore, the thresholds are met, and we are good to go. So that is what I got. This gives us, again, the mean, standard deviation, and we know its shape. That is 7.2 work. Everything beyond that is going to be Chapter 2 work. So I know it's approximately normal curve. I know it's centered around 0.75. And then now we start to ask the question. Find the probability that a random sample of 1,000 young adults, right? That's what we've been working on. We're creating a sampling distribution for samples of size 1,000. And it will be within 2 percentage points of the true value. So that means it's going to go as high as 0.77, and it's going to go as low as 0.73. Right? So within means give me the area right here, that it can be as high and to as low as that. So then what do we need? We just need a normal CDF. Normal CDF, and I'm going to put 0.73, 0.77, 0.75, and my new standard deviation that I calculated, there it is. All right? So let me give it a go. 0.73, 0.77, 0.75, 0.0137. And I'm going to get a probability of roughly 0.8557. And that would give us the answer right there. So that's what we're trying to do. We got 7.2 work. That's the setup and the checks. And then you got Chapter 2 work, which is solving normal curves. Once you have set it up using your Chapter 7 stuff. All right? That's what I want you to be able to do. Push through, get some of those assignments on Khan Academy and My Open Math done, and we will see you on the next class. All right?